Okay, so today we're going to do two problems: edit distance and matrix chain multiplication, and then I have some extra exercises queued up at the end if we have time just to practice. But in particular, we're moving beyond, or I don't know if it's beyond, but we're doing the thing after divide and conquer now. It's going to be something called dynamic programming, which is a very practical thing. And the way it's organized, we're going to do kind of one lecture on dynamic programming today. Then we're going to do a couple graph stuff for the next two lectures, and then we'll come back to do dynamic programming again. And it's going to be kind of recurring. So we won't necessarily do like 2 or 3 straight weeks of this kind of thing, but it's going to repeat and kind of be an ongoing thing. So this is, and you'll get like an infinite number of practice problems in this space because it's something that you can really master. So, all right, so let's see. We'll start with this edit distance stuff. So I suppose all of you use something like GitHub, maybe. So GitHub, you check in your files and it organizes things for you. It also has pages like this that'll show you, between two commits, what are the differences, right? So I guess this is many years old now, but this was some GitHub when I was using for the class or something a long time ago. Okay, but you can see that the line that got replaced was like went from red to green or something. We've all seen this before. Do you know the name of the algorithm? It's like a Unix tool that they use to kind of generate these summaries. Yeah, diff. Okay, so diff. Diff. This is the man page for diff. And so we can read it. You're comparing files line by line. You can ignore cases or blank lines or some configurations. But the goal of diff is to give you a very compressed summary of what are the differences between two files. And what it wants to try to do is somehow try to match up the lines that are in common so that it can kind of there's many ways to try to describe the differences from one file to the next. But it really wants to come up with sort of the smallest summary so you can kind of most clearly see things. Okay, so we're going to kind of discuss the algorithm that's underlying this tool. Okay, so another application or another reason to kind of compare strings besides source control. So I'm sure we have people who work on this computational biology kind of problem. But this is, of course, like DNA, right? So I'm not an expert, of course, but we're made up these DNA, which are like these long sequences of 4 letters, A, C, G, and T. And it's somehow some kind of code that somehow describes how we're put together and things like this, right? So whatever, I'm not here to lecture about DNA, but it's a very common task in computational biology to take two DNA sequences and try to compare them. Okay, for our purposes, they're just sequences of letters. You want to compare them. You want to know if they're very different, if they're very similar. This can be useful, like for analyzing hereditary traits or something. You have 2 siblings, but one got sick, one didn't. Maybe they have some slightly different letters or something. I don't know. I guess I also wrote distinguishing species and stuff like this. So there is like a subfield that sort of tries to reconstruct a plausible evolutionary tree just based on whatever DNA samples they have. So if you imagine, some kind of tree and kind of common ancestors having maybe more DNA in common and things like this, and they have some kind of, criteria to find the most plausible tree given the evidence they have. And of course, it's tough to do because most of the things in the tree are long extinct, and it was only small traces left behind and stuff. I don't even know what I meant by this, but I wrote tracing lineage or something. I guess it's sort of evolutionary tree stuff, but whatever. So computational biologists often do this, comparing DNA strands, trying to figure out the differences. They want a compact description of the differences. Okay, so I'm going to present 2 different ways one might measure the distance between 2 strings. The first one comes up more often in error correcting codes and certain engineering disciplines. It's called the Hamming distance. It's maybe the most natural thing that'll come to mind. So Hamming distance is really only defined, at least naturally, when you're comparing two strings of the same length. Okay? And or there can be, bit strings because they're like codes, or they can be whatever. And the idea is that you're going to line up the two strings, first, second, third, fourth, fifth, and just see how many mismatches there are. How many locations where, the 10th location they have different letter, 20th location they have different letter. Okay, that's called the Hamming distance. For example, in error correcting codes, they often talk about some scenario where you are trying to transmit a bit string, and then as you send it over the wire, some bits get flipped. Right? Number of bits getting flipped, that would sort of be the Hamming distance between what you tried to send and what got sent. Okay, so for example, in this, I guess, little example here, I have A, B, C, D, E, F, G on top, A, B, C, E, F, G, D on the bottom. What is the Hamming distance between these two strings? Yeah. 4. Okay, which 4? Yeah, the last 4 are all off. Okay, and you get a Hamming distance of 4. Okay. Nothing deep, just want to make sure we're on the same page. Okay, so that's one way to try to compare distances between strings. Here's another one. It's called edit distance. This is what we'll end up focusing on. So another way to maybe compare strings, imagine you're at a keyboard typing, right? And you want to convert one document into another. How many keystrokes do you need? How many characters do you erase? How many characters do you insert? Maybe you select and replace some letters. Okay. So the edit distance will be, just going from here to here, the minimum number of operations you need to convert one from the other. The operations are inserting a letter at some location, deleting a letter from some location, or replacing one letter with another. Okay, so 3 operations, they all count as 1. You could give them different weights, but we'll count them all as 1 for simplicity. And your goal is to just compute this minimum edit. It's called minimum edit distance. Okay? So here's the same 2 strings as before, which had Hamming distance 4. What would be their edit distance? 2. Okay. Anyone else get 2? Okay. So what are the edits? Yeah.
Delete the D and X.
Yeah, so we're going to delete this, and then we're going to kind of insert this. I guess you're converting X, so it kind of gets inserted into there. Okay, so here you have an edit distance of 2. Okay, which in this case might be more natural because clearly all I did was replace and move the D around and otherwise change the color. Okay, so if I were to compare these two, oh no, we'll compare in a moment. I guess I just wanted to make this one point. So both Hamming distance and edit distance give what's called a metric in a certain mathematical definition of metric over strings. Okay, Hamming distance just for strings of the same size. Maybe there's some math majors in here. Does anyone know kind of the definition of a metric, the formal definition, the properties? So the general motivation is, we're comfortable with things like distance in Euclidean space, right? Like this is however wide this is and things like this. And we're used to kind of normal geometric distance in physics. But what we want to do is identify like a couple simple math properties that sort of behave like Euclidean distances. And it's very helpful, right? Because then I can start talking about distance between strings or things that are not like physical distance, but we can kind of use the same language and same intuition when discussing them. Okay, but I'm sure some people have seen, yeah. All right, so let's go one at a time. Let's see if I remember. So the first one was positivity. Actually, I had this breaking down into 2. So one is non-negativity. So if I'm proposing some distance between some objects and I want it to resemble how I intuitively think of distance, natural requirement, okay, everything should be non-negative, right? I don't think of negative distance in real life. And then sort of folded into positivity would also be, the distances between 2 points should be the same only if they're the same point. Okay, so it's positive for all the distinct ones, non-negative in general. They can be equal if they're the same point. And then what were some of the others?
Symmetry and
Okay, so symmetry. So that's also an intuitive thing, right? The distance from point A to point B is the same as from point B to point A. There's no orientation when we talk about normal distances. We want that also to be true for anything we call a quote unquote metric. And then the last one is the triangle inequality, right? So, this is like, yeah, okay. So if I'm just trying to get from point A to point B, right, or the distance from point A to point B is less than equal to pick any other point C. If I sum up this distance and sum up this distance, like two sides of a triangle, it'll always be at least sort of that direct hypotenuse or whatever. I forget my terminology. Okay, but that's a triangle inequality, which also kind of makes sense as the word anyway. So it's easier to verify that Hamming distance satisfies this because Hamming distance is not that different from Euclidean distance because you're just kind of seeing if the bits are equal. That's a lot like saying x1 minus x, or comparing x coordinate, comparing y coordinate, comparing z coordinate, right? But edit distance is a little bit funky because that's not like such a clear, oh, you're comparing two vectors or something. So maybe it's worth just to build, make sure we're on the same page, checking that the edit distance will satisfy these things. So first, why is edit distance non-negative? Yeah.
We haven't defined the negative edit.
Yeah, there's no edit. It's just number of edits, and kind of number is inherently a non-negative quantity. What about this kind of zero if and only if they're the same?
We don't edit anything.
Yeah, okay, that sort of follows, right? If there's no edits to take you from string A to string B, then string A is string B. And if string A is string B, you don't need any edits to convert them. Okay, so that's fine. What about symmetry? Is edit distance symmetric? Yeah.
If you think of opposite of the edits that we did to get from A to B, then it would have the same opposite edits to A to B.
Yeah, so there's almost a sense of like reversibility, right? If I'm doing an insert if I'm trying to go from A to B and I have to insert a letter from B into A, that's sort of like deleting from B or something like this, right? So the inserts become deletions, deletions become inserts, the swaps just get, right? So if I can take 10 operations to go from A to B, there's some kind of reverse thing where I could take 10 operations to go from B to A. Okay, so it's totally symmetric. And then finally, what about the triangle inequality? The triangle inequality says, yeah, this kind of intermediate point thing, right? Why would the triangle inequality apply for edit distance?
Because like distant x and y is already like the smallest distance, so like distant x, z and distance z to y is also like edit from x to y, so it has to be greater than equal to like the smallest.
Yeah, so it's really built into the word minimum, right? So this is the minimum number of edits to get from string x to string y. Suppose you had some other string z, and you did the minimum number of edits to get from x to z and some edits to get from z to y, right? So there's some sequence of edits and some sequence of edits. If I concatenate that whole sequence, they'll end up going from x to y. It goes through z, but ultimately I can take those two sequences of edits. How do I get from point A to point, x to y? Well, you can go to z first and then, right? So I can take the edit sequence going from x to y, x to z, sorry, and then the edit distance from z to y. Put that together, I get some edit sequence going from x to y. Okay, and this is just defined as the minimum. So always be less than equal. So because this describes some edit sequence from x to y, and this is the minimum tally over any edit distance, that's where this less than equal will come into play. So it's really the word minimum is doing the work for you, besides observing that two edit distances can be kind of combined, or two edit sequences can be combined. Okay, so this is very, very nice. I mean, in practice, if you're actually talking about genomes or code or something like this, you can kind of talk about it as a distance, and a lot of your intuition from just normal physical distance will carry over. Okay. Of course, this is not a math class. This is about algorithms. Now, okay, so maybe just to really drill into the differences, I made a pro and cons table about these two distances. So I would say maybe a con for Hamming distance is that a small misalignment can lead to a huge Hamming distance, right? So you have a piece of code and you delete one minuscule line in the middle of the code, everything shifts up. Your Hamming distance will just explode. right? Let alone the fact that it's different distances which causes another. Okay. But it'll just explode. But in your mind, you only made a very small edit. So Hamming distance probably isn't very intuitive for you. My understanding is that actually photons can also hit like DNA sequences and just like knock out a letter and things get misaligned, but that's just something I read somewhere once. Okay. But anyway, so misalignment causing a huge distance may not be what you intuitively have in mind for many applications. I would say the pro though is this is very easy to compute, right? If I just want to get the Hamming distance, I just line up the strings, boom, 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 boom. There's no algorithms class necessary. Okay. All right. Now, if I go to edit distance, I would argue that for at least, a lot of applications, this may be the better model of distance between strings, right? I do, at least obviously for code, really think about how many edits are needed to take from one piece of code to another. Okay, so there's maybe a lot of applications where edit distance is just more sensible. The value, that quantity means more to you than Hamming distance would. But the cons, and the part that we'll need to address, and that's clearly more complicated, is some kind of like existential, minimum distance kind of definition. And it's not at all clear how to even compute this. Okay, so as intuitive as the object is, the thing we're trying to compute, that seems like the right model. It's like, what are you going to do? Brute force the whole thing? So that is the issue that we want to address. Okay, so good. All right. So the task then is to compute edit distance, come up with a good algorithm for computing edit distance. And we're going to start with a recursive algorithm because that's just what we do. Okay. So the first thing we're going to do, as always, is just come up with a recursive spec. I see the groans. We're just going to come up with a recursive spec to first just define our problem. And that's going to be very useful when we start making a recursive algorithm. Okay? So I gave us a name, but we need parameters, we need a sentence. Again, it may not be doesn't have to be a clever sentence, just a sentence. Yeah.
Given a string, and assuming the string, it's like and returns the edit distance of
All right, so maybe something like given two strings, X and Y, returns edit distance between X and Y or something like this, right? This is again another one of those out. We're just restating the problem from class. It's not too clever. I think PSO will at least give you a couple problems where it's actually helpful to go slightly beyond the original problem statement. But this one, I think this will suffice. That's basically what I had prepared. I guess I opened up what edit distance means a little bit, but it's the same thing. Returns the minimum number of edit operations needed to convert X to Y. Okay. All right, so nothing special there. We haven't done any deep thinking. Okay, so now let's implement it. So I'll set up the header for us. Okay, so you have one string X of length M, one string Y of length N or something. Okay. And now we just want to try to implement edit distance. Any takers, any ideas? We can start small. What are some easy? Yeah.
For the base case, we could have this N0 in return.
Yeah, so if M is 0, so there's no X, we'll just return N, the length of Y, because you have to insert all of Y. If Y is empty and N is 0, I'll just return M because you have to delete all of X or something. Since I'm really lazy, I'll write if M is equal to 0 or N is equal to 0, I'll return M plus N, which is just folding those together. Okay, nothing special. I usually discourage like being clever, but my handwriting's so bad, I want to just write as little as possible. Yeah.
Why does it say X to
Oh, it's because it's supposed to be a 1. Yeah. Your instructor has a handwriting of a 7-year-old child. Okay. Good. All right, so that's a start. So that's the base case, right? At least if either string is empty, it's just kind of the remaining length. So that makes sense. The interesting remaining case is when both strings have at least one character. And the basic task to make a recursive algorithm is try to figure out how to turn this into a slightly smaller problem, right? If we can just chip away a little bit and it kind of fits the recursive spec, then we're just done. So we just need to nibble away a little bit at it and we'll have it. And don't worry about being an efficient algorithm. We'll address that later. We just want to first make a correct algorithm. Yeah.
If the first character of both strings match, then you can start with the second character.
Okay, so this is kind of intuitive. So we imagine, I think from your point of view, two strings. But let's just start at the front. Just go from left to right. If these two characters are the same, that's something I can kind of set them aside and just figure out how to convert the remaining n minus or m minus 1 to remaining n minus 1. It's a tradition of computer science to always choose the letters that look and sound the exact same to create maximum confusion. So, but the suffix of the first was the suffix of the second. Okay. All right, so that makes sense. If x1 is equal to y1, return. Okay, so I'm just going to force you all to fill this in. So I want to recurse on, we said, the suffix. So that might start from index 2. That's supposed to be a 2, but it looks a lot like a 1. And y2 up to n. Okay, so when they're matched, I can throw them away and then just worry about the rest. Okay, so that means in a remaining case, they're not equal. x1 does not equal to y1. Yeah.
Three things we can do. We can turn x1 into y1. We can add y1 to the beginning of x, or we can delete the first thing x.
Right. Okay, so we're going to keep focusing on the beginning. Okay, so there's a whole sequence over there, but I'm comparing x1 to y1, and they're different letters. And at some level, the first letter of the x eventually needs to be this one down here, and it can't be this one. So I can either delete it, because the first letter can't be x1, or I can insert y1, or I can just rewrite and replace x1 with y1. Either way, that'll get the first character to be y1. Or either, you can't have it be x1 and not, okay, anyways. So, okay, so somehow, this is not a real code yet, but, so you said, okay, either we sort of, maybe let me write it out in code. You either insert, or as comments, you either insert y1, you delete x1, or you replace or substitute x1 with y1, right? So we've broken it down into 3 steps. Now we want to turn it into code. Yeah.
So you can just take the min of the edit distance.
Okay, good. Okay, so hold that min thought for a moment. So first, if you want to simulate inserting, that needs to map to some kind of recursive call in some quantity, right? So how can I write or model inserting y1? Yeah.
You like want return 1 plus edit. Max it 1 to n. And you want it to get that.
Okay, so this will model inserting y1. So, okay, you insert a y1, so you don't have to worry about y1 anymore. So you can work on the rest of y. Okay, and then you did pay 1, so you got to remember to add the 1. This represents the part where you inserted y1, and that's why you can advance along the y string. And x we haven't changed yet. The beginning of x, except for that y1, x is still the same. Okay, so we only advanced one of those. So now this might be easier to guess because it's sort of symmetric, but how do I model deleting x1?
1 plus x starts from 2.
Okay, 1 plus, this time x is starting from 2. Okay, so the 1 represents the actual deletion. And again, this time, looks like that's supposed to be a 1. Y has not changed because we didn't insert Y1. And then finally, how would I model replacement? Yeah. This time they're both starting from 2. So I just set x1 to be equal to y1, and I just have to worry about the rest. Okay. Okay, so that would be modeling the 3 options, right? This will recursively figure out the best way to go about it if I inserted on the first one. The next one will figure out inductively the best way to do the rest if I deleted. And then this will inductively figure out the best way if I substituted. Okay? But now to bring it all together, Thomas had said this, but I'll ask again. How do I I don't know which one, right? It's not clear if you should insert, delete, or substitute. Yeah. You take the min. So all you know is whatever is the optimum solution has to do one of these 3. And you might be tempted in other years, sometimes it'll be suggested, okay, maybe I can look at the second character, third character, and do something clever. And based on that, I know I should insert a deletion or something like this, right? You can imagine maybe doing a lot of strategies. But we're not doing any such cleverness, and those won't actually help you. All we're really saying is, look, whatever is the solution, it has to do one of these 3. So let me just enumerate and capture them recursively. By induction, this will do the best one if you had done insertion. By induction, this will get the best one if you had done deletion. By induction, this will get the best one if you had done replacement. You can't do better because it's smaller. I know it's going to be perfect. I don't know which one to do. I'm just going to return the min, and that'll be at least as good as whatever the best solution is, right? So we're not really aggressively saying anything clever about the best way to do edit sequence. We're just saying, there's only so many things you can do, and I can just enumerate them. Yeah. Yeah, okay, so time complexity is an issue, but at least as far as correctness goes, this is like a very conservative, not trying to be too clever, recursive kind of induction algorithm. I guess by now you've had a fair amount of practice with this, so it's not too surprising. Okay, so that's basically what I had. Maybe I'll only make one comment here. It is true that if you look carefully, if x1 is not equal to y1, you should just go ahead and recurse on the remainder. But then when it comes around to time to writing a proof, you'll need to write a paragraph justifying, okay, if they're the same, then this is why you can get away with just recursing on the remainder. So if you're really lazy, as I am, and you don't want to write this extra paragraph of justification out, you can just do the conservative thing. Here, if x1 is equal to y1, I went ahead and listed the other 2 options anyway, so that I don't have to justify that they're unnecessary. So it will ultimately, you just need this line. This is the line we did together. But I felt like, okay, I could either just go ahead and enumerate the insert and deletion options, or I could write like an awkward paragraph trying to explain why it's okay to get away with it. And this is much easier for me. Okay, so sometimes, okay, it's just a constant, you don't care. So sometimes you can just take the easy way out. Okay? Either algorithm, of course, be correct, but it's just, a trick. Okay, now here comes the point that was just raised. What is the running time of our algorithm? So I think we feel good about the correctness of the algorithm. It's very conservative. It's basically enumerating everything. It leaves nothing out. We only make the observation that you have to do something to address the first letter. That's correct. We're okay with that. The rest is inductive correctness. We've been doing that for 2 weeks. So correctness of the algorithm is fine. The only issue is running time. So first, let's model the running time recursively. So T of n will be the running time for n inputs. And what does our algorithm look like as a function, kind of recursive function? Yeah.
Like 3 times n minus 1. 3 times t.
Yeah, in fact, I don't feel like I did a very good job here. Oh, what am I doing? Okay. Okay, so if I guess you have to be a little bit clear. I don't know why I did one variable. One could also do 2 variables. Maybe one variable easier to do the math. If I let n be the combined input size, k plus l, okay, then your recursive subcalls are, going from an input of size n to maybe 2 problems of size n minus 1 and 1 problem of size n minus 2 or something. So it looks something like 3 I keep writing 3. Sorry. It'll look something like 2 tn minus 1 plus tn minus 2 plus a constant. Something like this. Okay. And so these are recursive calls where you just remove one letter. This is a recursive call where you remove one from each. N is the combined input size. I could have done K comma L separately, but I think this will be easier for this math. Yeah.
For 3, did you make the order in seats?
So you can do just A when it because it's almost intuitively clear. But when it comes time to write a proof, you would need to write a paragraph saying, okay, if x1 equals to y1, let me prove to you that you don't have to do these 2 steps. So you can do it, but it will require some care. If you're doing a non-trivial step, then you need to kind of prove and justify it. Whereas I didn't want to write that paragraph, and I said, okay, let me just be safe and enumerate it, even though I know it's not necessary. I mean, in the back of my mind, I know it's not necessary, but I don't really want to do it, write it out. So you can do either one, but if you do something non-trivial, you do need to justify it. That's the only thing to point. And there's a lot of situations where you don't really have to be that clever if it's all going to hide in the big O notation anyway, right? So it's sort of like telling the forest from the trees and just focusing on what the real issues are. Yeah.
Can you give like a really brief explanation of why you can just do edit by itself and why you don't get rid of it?
Yeah, it's okay. If I was going to try to prove that you can skip B and C, I would say like, okay, take any optimum. So it'll be kind of wordy and awkward just to say something that should be very simple. Like, I think just watching me struggle will make this point clear enough. It's like, okay, suppose I had any optimal edit sequence. If it did substitute x1 to y1, then recursively I know that the remainder, I'll capture the x2, y2. I'll do the rest optimally by induction. But if the optimal edit this sequence did not do a substitution for some mysterious reason, right? I mean, it shouldn't, but it could. Then I'll be like, well, okay, they must be inserting or should be deleting or something. And I should be able to take, let's suppose it inserts. I should be able to replace that insert with a replacement, and that'll be the same sequence length. Okay? Except it's going to be a little awkward. Okay, so you find yourself in a situation, say, okay, suppose the optimum solution inserted instead of doing the obvious substitution. Okay? And then what I'm going to say is I'm going to try to convert it to an edit sequence that does substitution first with the same length. And that will prove there's always an optimum edit sequence solution that's substituted first. Because I can take something that didn't substitute and give you a different edit sequence that does substitute with the same length. And then I imagine getting into something like, okay, suppose it inserted y1, then I should be able to, intuitively, I want to be able to say something like, oh, well, I should be able to, replace that insertion in the log with a substitution, and it'll kind of be the same. Except it's like, oh, now what if this substitution, is like, that character was getting matched later on or something like this? It's a mess. I feel like there's a better way to do this, but it's not coming quickly to me. So it is definitely doable, but I kind of forget how to do it nicely and cleanly. In any case, it'll be an exercise to get it down right. Yeah. But at a high level, what you want to prove is that there's always an optimum edit sequence that does substitution first. And so you can say, oh, well, suppose you're given an edit sequence that's supposed to be optimum, but it didn't do substitution first. If you can convert it into another edit sequence that does substitute first with the same length, that will prove the point. And I think there's a more elegant way to do it than I'm coming up with, but in any case, it's not. It'll take some concentration. Shouldn't be that bad. I'm sure Wikipedia just lists it out. It's not that bad, but I can't remember it. Okay. But the point is sometimes if it doesn't really affect the running time anyway, you can just be less clever and you don't have to prove as much. Okay. Now going back to this running time, we have a recursive running time like this. And I actually, it's going to be pretty bad running time. So I want to suggest it's bad, although it's slightly awkward because you have this 2n TL. So anyway, anyone want to give some lower bounds, sloppy lower bounds on the running time? So for example, what makes this awkward to look at? Yeah.
Not really true to the end, so you're taking 2 TN minus 1.
Yeah, so you might have been looking at this and be like, well, I got 2 Tn minus 1, that would be easy. But this Tn minus 2 is kind of throwing a wrench in it. You're like, how do I deal with both? If you're trying to do a lower bound, okay, let's just drop this, right? If I told you this was the running time, this is less than the running time, then you would recognize this to be at least. So I have n, and it'll double, it'll double, it'll double, it'll double, it'll double all the way down, but we're only going down by 1, right? So how many levels would there be until I get to 0? And each time I'm doubling. So how many like total leaves will I end up with? Like 2 to the n. So you end up spending at least 2 to the n time, and that's even omitting one of these, one of these recursive calls. Okay. So, it would have been, 1 plus 2 times Tn minus 2, that would become 4 times Tn minus 2, 3, and so forth. So this is an exponential running time, and that's not too surprising. It's just brute force. Okay. We did take some observations to structured brute force to kind of go from beginning to end. Okay, but we're still basically doing brute force. For that reason, we feel very good about its correctness, but we don't feel good about its running time. Yeah, so let me summarize. All right, so first, edit distance is a good model. I would like to have an algorithm for this. I can think of applications where this is the right thing to do. That's okay. It can be computed recursively, but the recursive algorithm, the natural recursive algorithm, does take exponential time. Okay. So the basic question is, can we get the best of both worlds? Or at some level, is there a way out? Can I keep my correctness, the clear, obvious correctness of a brute force algorithm, just trying everything and kind of enumerating everything, so it's going to get the right answer. But we try to make it efficient. Any ideas? How can I take our obvious correct algorithm and make it efficient? Yeah. Yeah.
Why is it on the last slide 2 Tn minus 1 and not 3?
Yeah, so I used, so why 3 and not 2? And then it's a little inconsistent with the next slide. It's here I'm using L to be the combined lengths. And for some of these, like this one here, where I remove 1 character from each, we actually lose 2 from the combined length. So instead of going to n minus 1, we're actually going all the way to n minus 2. So that's one of these calls is n minus 2, the other 2 are n minus 1. So this one, I'm just dropping 1 character from x. This one, I'm dropping 1 character from y. That's a 2 Tn minus 1. This one, I'm dropping a character from x and y. So that's Tn minus 2.
So what about the top 3? Do I think x1 is not equal to y1?
Yeah. Yeah, it's like out of order for some reason. So sorry for that. But here in the first row, I'm dropping just 1 from x. So that's a Tn minus 1. Second row, I'm dropping 1 from y. That's Tn minus 1. Here, I'm dropping 1 from x and y. Tn minus 2.
Oh, I see. Every time the function is called, only one of those blocks run.
Uh,
Both times it's the same. It's 2.
yeah, as opposed to like 6 or something. Yeah, we'll only go through one of these if else branches. But even just going through one, we still have a pretty painful running time. So what I have in the bottom here is not quite right. It's a little bit more detailed than that. It's 2 Tn minus 1 plus Tn minus 2, but it's basically the same conclusion. Okay. In any case, it's an exponential running time, no matter how careful you are about the accounting. Okay. The clear virtue is that it's a simple, the correctness is relatively simple from induction. If you just observe that, okay, something has to happen at the beginning. Okay, so correctness is not an issue. The only issue is running time. If we could just make this efficient, right? Yeah.
I noticed that the running times, there's only like nice there of the like and this you can call it that is.
Okay.
So it's like you're doing like different types of.
Yeah, so is there something wasteful about this algorithm? This is like, think about the recursive algorithm, right? Like maybe you first insert and you chip away at the y, and then you delete, you chip away at the x. Now you're looking at the subproblem as 2 and 2, right? Or you could have substituted and gone there. Or you could have like deleted and then whatever's the opposite one, right? There's 3 different ways to get to 2 and 2. Right? If you pick somewhere in the middle, like 10, there's only like 3 to the 10 ways. I mean, there's a ton of ways to end up at the same subproblem. So this, you can imagine like a big recursive tree of subproblems, but actually a lot of the nodes are identical. They're all taking different paths to the same subproblem. So if you look at this, you're like, oh, why am I solving the same subproblem twice? Like if I on the homework, like repeated homework problems, you'd quickly catch on and be like, I'm not doing that again. I'm going to copy and paste, right? So this recursive algorithm is a little bit clumsy or heavy-footed because it's actually resolving the same problems again and again and again and again. So it was pointed out that, at some level, how many distinct subproblems even come up over all our recursive calls? And why?
K times example.
Yeah, k times L, I guess with respect to the original input, m times n, but where's that coming from? Why is it m times n? Yeah.
That's comparing every letter in X with every letter in Y.
That is comparing every letter in X and every letter in Y. Yes. But to me, that doesn't, well, okay, yeah, maybe that counts because we're always looking at the first 2 letters. So, but at some level, all our subproblems are some suffix of X and some suffix of Y, and then the first 2 get compared. So some suffix of X and some suffix of Y, given by their indices, right? And there's only so many suffixes. There's M suffix of X because X only has M characters. There's only N suffixes of Y because the Y has only N characters. So there's only M times N distinct problems, right? So you're spending exponential time to only solve, mn distinct things. This is obviously wasteful. Okay. So what very simple hack, very CSE kind of technique, right? This is something a computer scientist will see, maybe not a mathematician. What kind of simple hack can you do to fix this? You have all this redundant work. Yeah. We're just going to cache it. Okay, so we're just going to save our answers once we solve a subproblem. Okay, we'll never solve the same subproblem twice. Once you solve something, write it down. When you come across the problem again, check to see if you wrote it down. Don't do the same thing twice. Okay? So that's all we're going to do. Okay. Well, there's supposed to be some stuff hidden, but that's okay. So the basic idea, first, just focus on the top. Maybe I'll go like this. Now on the bottom. We're just going to save the answers to every subproblem as we solve them and make sure we never solve the same subproblem twice. That's a very natural principle, right? You should apply this to like all things in life, not just your edit distance. Okay? At some level, all the things in real life do this, right? Like, all sorts of web servers cache everything. Why is your Google query fast? Because someone else already asked it and it was saved, right? So caching is a very natural thing to do. Okay, how could I save my answers? Yeah.
A hash table on X and Y.
Yeah, just make a hash table on X and Y. Any kind of table is fine. Technically, hashing uses randomization. So just to keep things clean, I'm just going to make an array, an m by n array, and just put it into the slots. We don't. Of course, in Python, you would probably just like put in a dictionary, but. Okay, so to make it a little bit more friendly for the table, I'm going to re-index our problems slightly differently. This is just a change of like notation. So what I'm going to do is, instead of just like recursively thinking of small subproblems, I'm going to just keep track of like the indices that start the suffix. Okay, so edit ij means I'm comparing xi to m to yj to n. So I and j are just these like intermediate pointers. Obviously, it's the exact same algorithm. Nothing has changed. Some arithmetic looks a little different. Now it's if I is greater than m to see if it's empty. Is j is greater than n to see if it's empty. Okay? But the algorithm hasn't really changed. I'm still taking the min over all these options. When I advance the problem, I advance I and j. But that just makes it a little bit easier to imagine constructing a table. Okay, so So outside of the recursive algorithm in some global space, I'll create an m by n array. Maybe initially everything will be set to null or something that indicates that it hasn't been filled in yet. Okay. And so I do that first, and then what? So it's the exact same algorithm as before, but when I get to this, interesting part, I first just check to see if I've already filled the entry in the table. Is it null? That means I haven't done it yet. If it isn't null, then I can just return it right away. But if it is not filled in yet, then I'll do the logic that we just described. Are they the same? Are they different? I'll do 1 plus this, 1 plus that, all that stuff. So it's the exact same algorithm. It's just wrapped in a wrapped in a table, saving your answers. I don't want to get too distracted. It's just kind of some standard scaffolding. Okay, but we'll just do that. It's basically a mechanical thing. Let's see what happens to the running time. Okay, so now we're going to account for the running time a little bit differently. Instead of doing like a recursive tree, what I'm going to do is I'm just going to think of all the subproblems. You never solve the same subproblem twice, right? If it's a lookup, it's just kind of constant time. So at some level, if I can just figure out the total number of subproblems and the time I spend on each subproblem, excluding the recursive calls, the work done in other problems, that'll account for all the time spent on this problem. Okay. So we already did this once. We'll do it again. How many subproblems are there? Sorry? N times n. Okay. And how much time am I spending on each problem? Just constant time. So if I'm not worried about the computation that's going inside edit I+1, inside edit, all these recursive calls, I'm otherwise just like comparing 3 things and summing up and adding 1 or something like this, right? So just constant work. So you're only spending constant time per subproblem, excluding stuff that's delegated to other subproblems. Okay? And that'll give you a total accounting of the whole thing. Okay? So you put that together, what's your running time? Mn. Okay? So suddenly we have an efficient algorithm for, computing this useful quantity, this edit distance between 2 strings. And the nice thing is, the algorithm in many ways is not that complicated. The original brute force algorithm was just, brute force enumeration. Maybe there's a little bit of care about whether or not you can just go with substitution when the first letters are the same, but whatever, right? The point is the algorithm is relatively simple. Naively, it's not efficient. But by just observing that there's a limited number of subproblems, it immediately becomes efficient, right? So this is a very generic recipe. This is not particular to edit distance. Any situation, yeah.
Does the space complexity blow up from this or
Okay. So we can talk about how much space we use. That's not a major point of emphasis, but how much space do we use? Yeah. M times n.
does the recursive stack have any play in space complexity, or do we just ignore that?
There's a recursive, yeah, so some level you can, well, first I wasn't even necessarily going to ask for space usage anyway.
Sure.
So because your space usage is always going to be bounded by your running time. So that's always a safe one because you can only write one thing at a time. And if you actually want to go through this question of your recursive stack, okay, I mean, I guess you can take a path of length m plus n all the way through your stack. And that's just like additive on top of the mn. It doesn't get multiplied with mn or anything. So I think now I think about the recursive stack won't be significant because it's just tracing a path of length m plus n through your i's and j's. And it's that, yeah, so it's not that big a deal anyway.
So do we just never care about space in this class?
Yeah, basically. It's not the point of emphasis. Some people will want to. There's a couple problems where you can occasionally be very clever as you fill out your table and notice that as you fill out one row, you only need the one row below so you can like save some space because you don't need all the other rows. No one cares. It's not important. Okay. Yeah, so we won't point that out, although, you'll see some whatever puzzles online that point this out, so you should at least be aware that some people care, just not me. Yeah.
Can you take this idea a step further and just say, like, if since we're interested in the minimum distance, then like if a path brings us to about a distance that is higher than what our current minimum is, then just abandon that path.
Yeah. Can you abandon that? Okay. Can you bake in heuristics where you can keep track of your best solutions so far and cut things off? I mean, I think in principle the answer is yes. Now, with a problem like this, right?
Is that better or worse?
Well, you're not going to be able to prove anything better in the worst case because you don't know which path gets you to the solution. That's why we're just enumerating everything in this conservative way anyway. If we had a stronger sense of like, well, you should just do this and ignore this, then you would just do this and ignore this. And in which case you don't have to even do some of this stuff. So an algorithm like this, you just don't have enough structure to know that you can always cut off a lot of computation. So yeah. So at least on paper, it won't buy you much. Certainly heuristics in real life is totally fine. Okay. Good. Okay. So again, edit distance is just an example. This whole situation where it's like, oh, I know how to solve this recursively, and I noticed that there's only a small number of subproblems. Oh, suddenly I have an efficient algorithm. That's this generic thing that's sometimes called dynamic programming, which is a ridiculous name, with ridiculous historical origins. But yeah, very simple idea, right? Small number of subproblems, save your answers, now it's efficient. Okay. The real hard part is just identifying the subproblems, right? There may be different ways to take your problem and structure into subproblems, some of which comes out to show only a small number of subproblems. Others are just like wild and crazy. Okay. Like it was very helpful with the edit distance that I'm just picking off from the front, so I'm only looking at suffixes. We could have gone on a different tangent where someone suggested, well, I could try inserting something in the middle and deleting from the middle and things like this, right? And then your subproblems will start looking like these holes with arrays, or arrays with holes, because you just replace like one letter from the middle and now there's some different array, right? Suddenly you'll have like exponentially many subproblems because on the X side, you've like dealt with some arbitrary subset of letters, and on the Y side, you dealt with some arbitrary subset of letters. There's 2 to the M different ways to do the X. There's 2 to the N different ways to punch holes in the Y, right? So that wouldn't be compact. But noticing that you can work from beginning to end, that naturally gave you the small number of subproblems. Okay? So sometimes there is some challenge of figuring out the right inductive structure that leads to a small number. Conceptually, that's maybe the real thing. Figuring out not just how to break it into smaller pieces, but those pieces you want to be organized in a way that naturally leads to a small number of subproblems. That's really the critical task. Sometimes there's 1 or 2 tricks you can throw on top, but those are, small things. So in this class, and this is not conventional for all classes, but in this class, we're only going to stress certain steps. Okay, you can guess the first step. Okay, so the first thing you got to do is you got to write a recursive spec. Like you'll see every answer key, this will be like half the points or something. But you'll find that if you get the right recursive spec, you're probably going to get the rest of the problem right, assuming you took your time and you slept enough the night before and stuff like this. Okay. The next step is to just write the recursive implementation like we did, the naive recursive implementation. Don't worry about caching. Just the one that's clearly correct and easy to read. All I care about is that it's easy to read, it's conceptually correct, it's implementing a recursive spec. I should be able to understand the correctness using your recursive spec as an inductive hypothesis. Now, something you may find is that you first come up with the most natural recursive spec, just basically restating the problem. And you might find that your subproblems, it's hard to implement. Okay? You might find, and you'll get some exposure to this in PSO. Hopefully you're going to PSO. Otherwise, you'll find out the hard way in homework. You might find that if you strengthen your recursive spec, where you actually try to do a little bit more than initially asked for, then the nice thing is that in your recursive subproblems, you're getting more. Okay, so keep an eye out for this, that sometimes you can play these games with recursive spec where you make it a little bit stronger. It's something a little bit different than immediately asked for. And that actually makes it easier to implement because you have the stronger subproblem. Okay, so just keep an eye out for that. We'll get so much practice that it won't be so daunting. There'll be a lot of practice. Okay, so spec implementation, by now, if it's done correctly, you have a very clear idea what's going on. So now it's just some accounting. Okay, so as we saw, the part where we saved the answers was completely mechanical, right? We set up a table, we fill it out. It's like this for every problem. So we don't want you to write the code with like a table layered in and we have to kind of ignore all it just to see it's correct. Okay, so just write the clean recursive algorithm and then just write the word dynamic programming or write the words caching anywhere. You can put it in a sentence, you can put it in the corner. Just put those words there and it will automatically infer, okay, you can just layer on caching on top and make it easy so we can just focus on the correctness. We can check your base cases are correct and things like this. Okay, so you don't have to write out the super complicated full system, just a correct kind of recursive algorithm and then just say you're going to apply dynamic programming. I think in Python, they have some memoize label that even does it for you. Okay. Beyond that, we analyze the running time, just like we did. And it's often not that complicated. It's often number of subproblems times time per subproblem. It's really total work over all subproblems. And sometimes there'll be distinction. But in general, this may be simpler than the recursion tree stuff. Now, our case was similar. Our case was simple because it was constant time per subproblems. There's some where maybe you have to do some scan over the array, so it's n time per subproblem. There's occasionally some tricky situation where instead of a full scan, you can do binary search, so it's log n, but those will come up and you'll have fun with that. So just analyze the running time because that's ultimately what we do in this class. Now, one thing to mention, worth mentioning, is so you make some recursive algorithm, you take some parameters, but there was some original problem. In our problem, the recursive spec basically matched the original problem, so there wasn't much gap there, but sometimes there'll be another gap. So make sure you're right, like, okay, if I want to actually solve the original problem, I plug in edit 1.1 and I return the answer of edit 1.1, because that'll give me the original thing, right? So this can be just very short, but basically how you actually use your recursive algorithm, your dynamic programming algorithm, to solve the actual original question. Here it might seem trivial, but sometimes there's a gap, so that will always be like 1 point out of 10 or something. Often not the hardest part, some kind of driver. There are situations where you might actually loop over and choose like the best initial starting point in some sense, but you'll see, things will come up. And then the proof is often not too complicated if you have a good recursive spec. It's almost always going to be by induction. It's always going to be like, well, you have to do one of these 3 things. Each of these choices by induction, I'm getting the best possible thing and return the min of this whatever best thing, things like this. So by the time you get to this point, especially if the right recursive spec, the proof by induction will be the boring part and you're like, why do I have to do this? And yeah, okay. But some proof ultimately almost always come from induction. Maybe there's some other details or something that requires justification in between. But at the heart of it, it will be a proof by induction based on your recursive spec. Okay. I think in this particular homework, we'll have 2 sequences of similar problems where we just want you to do a lot really fast and you can skip the proof by induction for these 2 kind of many problems. And I think the last word problem will be a lot longer and we'll ask you to do 1 proof by induction just so you at least go through the motions once. I think the first thing is to just have fun solving lots of problems first and then we'll make sure we understand sort of what's going on at a more principled level as well. Okay, my watch isn't working great. So, okay, let me point out the things we don't want, okay? Because if you looked up the answer on LeetCode or something, it'll give you all the things we don't want, and it's going to create a lot of confusion. So, we don't want the code implementing the caching, because that's automatic and it just distracts us from correctness, okay? We definitely don't want any iterative code building loops. It is true that for especially simple problems, you can imagine like building up the table from bottom up, but it's going to limit you ultimately. You want to solve the hardest problems you can with the tools. You don't want to burden yourself with this kind of order of operations, right? What really matters is conceptually breaking down the big problem into small problems, especially with a limited number of small problems. That's what actually matters. So we don't want this loop stuff. And if you give us loop stuff, we know you looked it up on the internet. At least I didn't teach it to you. And then we're not too worried about space usage in this class. Other classes might point it out. There are occasionally situations where you can do space less than the obvious number of subproblems. But whatever, that's just like some clever moment to say, it's cool, but it's not that big a deal. So we won't require it. Okay, but sometimes people do ask this, so maybe it's at least good to be aware. Okay, so that's it. So just those 6 steps and don't give us any of the last 3. Yeah.
The proofs change that you made
No, so you just have to prove the recursive algorithm without caching is fine, and the caching doesn't change any of the actual logic, correctness logic of the recursive algorithm.
So we can just like do like the regular inductive proof that we would have done. If we
Yeah, just a regular inductive proof. That's right. Dynamic programming is just for running time. This caching is just for running time. It has nothing to do with the correctness of the algorithm. Okay. I have some example, a fully worked out example in the textbook that you can pattern match or something. It's about as exciting as it looks. Okay. All right. 15 minutes left. So let me do any questions about edit distance though? Maybe I should take questions. All right, then let's do one more example of sequential dynamic programming. I have some extra, fun problems set up at the end if we have time, but probably won't. That's fine. So, okay, so when you multiply, two matrices, we did this a couple of classes ago, or maybe we did this last class, right? So this is a familiar formula. If I'm trying to multiply A and B, then for every row of A and every column of B, you kind of zip them together, multiplying pairwise. Right? And I'll give you one entry in the output matrix C. Okay? So if the dimensions were n1 rows, n2 columns in A, n2 columns in A, n2 rows in B, n3 columns in C, how long does this take overall? To get all the entries. Yeah, n1 times n2 times n3. So for each of these entries in C, that's n1 times n3, you do this loop of length n2 where you kind of zip them together. Okay. So last time we talked about faster ways to multiply two matrices together. Maybe that was a trick question because we now know we can do faster, but we're just going to assume this for simplicity. Okay. Now, look at something like this. Do I have anything written here? No. Okay. So here multiplying three matrices and the shapes will add up to give you something like this. Okay. And as far as correctness goes, I can multiply the first two together and then the third. Or we multiply the last two together and then the first, because it's like associative. Is that the word? Okay, it's some word. So it's associative. So as far as the output goes, it doesn't matter which pair of matrices you multiply at a time. But let's look at the different running times, right? We can take this as an example where n3 is clearly bigger than n2 and n4. So one way to do it would look like this. So I multiply the first two together. Okay, I pay some running time, and then I get this big matrix from multiplying these two together. And I multiply, this first and second combined with the third, and then I get the output. But overall, what does my running time look like? So here I'm paying, I guess, n1 times n2 times n3. Okay. And here I'm paying n1 times n3 times n4. Okay, so I'll put those together. So, this is just what it is. Okay. And if I did it the other way, right? If I did the second and third ones first, then your intermediate shape would look something more like this. Okay, so doing different order will get you a different, this is clearly smaller. Okay. And you'll end up, of course, with the same matrix. That doesn't change. This used to be, something's missing. Okay. But now when you, so first you pay n3, n2, n4, n2, n3, n4, just renaming it. And then you pay n1, n2, n4, n1, n2, n4. Okay. So here, these are just different quantities. Okay, so depending on whether n2 is bigger, n3 is bigger, n4 is bigger, n1 is bigger, you get different outputs. Okay, so you actually spend more time multiplying it one way over the other, depending on your dimensions. Okay, so our goal right? Our goal is to take something like a bunch of matrices where assume the indices match so that, they multiply, the syntax is okay, right? And our goal is to kind of figure out the best way to kind of multiply two at a time to minimize the total number of operations, assuming this, naive matrix multiplication algorithm. Okay. So one way to, you might like, oh, I'll do these two first, and then these two first, or second, and then maybe I'll do these two, and then these two, or something like this. I keep kind of grouping terms, two at a time. If it looks like three, that's because those two had become one already. So you can visualize, well, okay. I guess okay, so you can visualize, for example, I described it as bottom up, where you're multiplying two at a time at the bottom, but eventually it forms a tree, right? And at the root of the tree, you'll find all those original matrices, but they're all kind of wrapped in parentheses that tell you what multiplications you made along the way. Okay, so ultimately we're constructing, implicitly at least, some structure like this, and you want to minimize the total quantity of kind of arithmetic operations, those multiplications you're doing. Make sense? Okay, so I think there's a slide soliciting ideas. So any ideas? Yeah.
Well, first, as soon as you make one multiplication, you basically create a new problem where you have a new matrix, so you basically just reduce the whole number of matrices by one, so you can kind of recurse through that.
Yeah, okay, so we know that if I multiply two matrices together, I'll have a smaller number of matrices, and I can just recurse. Okay, good. So that's what is kind of what we want to do. We want to reduce it to smaller number of matrices, but do you want to be more specific about the algorithm? If you can reduce matrices, you can recurse. That's definitely true. Yeah.
At every step, you can either choose to multiply the first two matrices or multiply other matrices.
Okay, so you're imagining something going left, right, and I either multiply these matrices and then I can recurse and get the best thing that multiplies the first two together, or I choose not to multiply the first two matrices, and then what does my subproblem look like? Because that does look like it leaves a subproblem like this, right? And you could say, oh, put all those together as optimally as possible, and then I'll incorporate the first one I left out. But anyone see some issues? Yeah.
Like if the optimal one is where you multiply the left one by like two the ones on the right together, so then the one is to multiply.
Yeah, so maybe the optimum solution wants to multiply these two together, so the first one didn't get multiplied, but then afterwards immediately do this or something. And if you had kind of recurse on all the remainder, excluding the first one, that would kind of get left off because you would collapse everything and you wouldn't be able to explore this possibility. Yeah.
So it seems like the ones you want to do first is like where the matching size, for example, like the first two, like the two sides that are matching is the highest. And so you can kind of like do a search of like what is the highest like matching size between the two adjacent matrices, and so do that one first. And so each step would be kind of like a search. Like the matching.
So are you at some level also suggesting a greedy strategy? Is there something that I can kind of evaluate and just figure out the best split right away?
You have three.
Yeah, it's like, oh, can I do some greedy strategy that tries to focus on just minimizing the operations in that last step where everything comes together, right? But I think you have to be a little bit careful about downstream effects, because even though you're optimizing for the last step, that might make the intermediate steps harder. Yeah. Uh-huh. Okay, so you want to simulate this. So we need a fixed way to break it into parts. We want to break it into parts. Okay, so why don't we try to figure out the root effectively of this tree first? Okay, this is not so different than trying to figure out the last split, but it's going to be more aggressive because it's also going to take account of. So we know that ultimately there's going to be a final multiplication of two matrices, right? It could be split up here, where you somehow you multiply all these together, somehow you multiply all these together, and then you combine it at the end. Or the split could be here. You multiply the last two and you recursively figure out the best way to collapse these. But you know the solution will always have a split, right, at the top. That's sort of the root of your tree. And then you want to figure out the best way to do the two sides. And then add it all together, right? Okay, so that's what we're going to do. My watch isn't working. Okay, so, anyone want to quickly shout out a recursive spec? In particular, what do the subproblems look like? This is the most important thing. Yeah.
Given n matrices, return the minimum number of multiplications in both lines.
All right, given n matrices, yes. Now I want to index the subproblems though, because I want to make sure I have a small number of subproblems. So just like before, how we were working on two suffixes at any point in time, I'm looking for something a little bit more of that form. Yeah.
Maybe the index of where you're supposed to.
That'll be your choice. We will choose an index, but what will be the input? You're going to look at some subproblem. What does the subproblem look like? Okay, so originally you split, you have two subproblems that are two sides, right? It's it's the left side or the right side. Now I do another split. Now I have this like middle chunk. I do more splits, right? But as I'm splitting, all my subproblems look like, yeah.
Maybe advertise it's at over 2. Like elements. Simple.
Not quite. Yeah.
The starting index, the ending index, one matrices.
Yeah, so this time it's always a sub-interval of the matrices. So before we were always looking at suffixes, that's one kind of structure. Here I'm always looking at like, oh, array 5 through 10, array 6 through 7 or something. Okay, so as we do splits, it's going to carve out sub-intervals. And it's very important to point this out because how many intervals can we have? If there's like n arrays. N squared, you choose the left point, you choose the right point, that gives you intervals. There's only n squared subproblems. Okay. I realize I'm running out of time, so I'm just trying to be efficient. Okay, good. So this doesn't seem like much, but it's basically identified everything because the moment I wrote ij, and I've identified that the subproblems are characterized by the intervals, that's like 99% of the battle. You've now really broken down the problem efficiently. Because there's different approaches you could take in where you're punching out holes inefficiently and a bit of a mess. Once you realize it's intervals, life is going to be straightforward. If you're going to implement it, anyone just want to quickly shout out how you would implement it? Don't worry about the base case, no time for base cases. You have a subset of intervals. What are you going to do? Subinterval. Subinterval of matrices. Yeah.
For every k between I and j, recall it with I to k minus 1, k plus 1 to j.
So we're looking for a split. In the original problem, you're looking for a split, but in the subproblems, you're also figuring out where to split. You don't know which split to do. The greedy things are tempting, but stay away. So we'll just try all the splits, which will give different subproblems that look like intervals. Okay. That's all this code is doing, right? It's not that complicated. If there's no arrays, you just return 0. Otherwise, I'm trying all the splits. I recurse on the two sides. And this is the matrix multiplication that's coming from the last two being combined. Okay, so it's getting split between k and k plus 1, so that middle index is nk plus 1. Okay, so it's just brute force. And then there's not much else to say. To solve the original problem, you want to call it on 1n, right? Because that's the whole input. And I think all that's left now, if you apply dynamic programming, you never solve the same problem twice. We just figure out the running time and then we're out of here. So how many subproblems? N squared. How much time do you spend per subproblem? I guess the input is k matrices, but how much time do you spend per subproblem? O of k. So in general, it's the length of the interval. So you could be more aggressive, but you'll find that a constant fraction have length k anyway, so it's not a big deal. So you're going to spend at most k time, at least that's conservative, and you'll realize you're not going to do better by more than a constant. And so you get k cubed time overall. Okay, so this is a little bit different, way of decomposing the problem because we're decomposing along splits. That yields intervals instead of nibbling off the side like Pac-Man or something. Okay, so but that's the point behind this problem. Okay, so that's it. So in PSO, you'll get lots of practice with other sequence problems like this. They can be, well, in my mind, quite fun. But basically, if you just practice, this will become very comfortable much more quickly. Okay, thank you.